See, in the previous video, we were discussing how you may describe simple harmonic motion to be the projection of a particle, of a reference particle in circular motion onto the diameter of that circle. So if you now look at this triangle here, you see cos omega t plus phi is adjacent side x by a, where x is the instantaneous displacement of that particle which is executing the simple harmonic motion from the mean position. And a is the maximum displacement of that n, which is the simple harmonic oscillator from the mean position, which happens to be the radius of the circle. And we see that you get a function which is a function that we use to represent a simple harmonic motion. So let me repeat, a simple harmonic motion can be described as a projection of a particle in circular motion onto the diameter of that circle. Now this projection could also be taken along the y-axis, that is any diameter for that matter. Let me take this projection along the y-axis, that is the particle is here. Okay, this was our angle omega t plus phi. The projection is here n. This is the center. This let me call as n dash along the y-axis, and this displacement from here along this diameter, the vertical diameter, is what I am calling as the instantaneous displacement of the oscillator at any instant of time from the mean position. Now if I take sine omega t here, plus phi is opposite side by hypotenuse, which is a. This is our particle p. So opposite side will be this y. So that is equal to y by the hypotenuse is the a, the radius, and therefore we may write a sine omega t plus phi, which is again represents the displacement of the particle is represented by a sine function, which is a simple harmonic, which represents a simple harmonic motion. So the projection may be taken along any diameter, either any diameter for that matter. Okay. Now we may also represent. We will now discuss the velocity and acceleration of this simple harmonic, the particle in simple harmonic motion. So we have x is equal to a cos omega t plus phi, or velocity is dx by dt, which is d by dt of a cos omega t plus phi, which is, as you know, cos theta is minus sin theta. So we have minus a. If I differentiate this will be omega t. So this is a omega sine omega t plus phi. So this represents the velocity of the particle. You know that sine theta can be written as root of 1 minus cos square theta, because sine square theta plus cos square theta is 1. So I may write this as minus a omega root of 1 minus cos square omega t plus phi. Now cos square omega, we have x equal to a cos omega t plus phi, or cos omega t plus phi is equal to x by a. So I may substitute that here and write minus a omega root of 1 minus x square by a square, or if I cross multiply, this will be minus a omega root of a square minus x square. I have taken this a square outside so that it becomes a, and cancel this, and you have minus omega root of a square minus x square, representing the velocity of the particle, which means that when your simple harmonic oscillator is at the extreme position, this is x equal to 0, this is x equal to plus a, and this is x equal to minus a. So the displacement of the particle at the extreme positions can either be plus a or minus a. So when at extreme position, that is when x equal to plus or minus a at both extremes, the velocity of the particle will be minus omega root of this is square. So a square minus a square, and you see the velocity at both these positions are 0 at both extremes. Similarly, when x is in the mean position, when the particle is in the mean position, that is when x equal to 0, the velocity of the particle will be minus omega root of a square, or that will be plus or minus omega a. Plus or minus, because a can be taking plus or minus values. So the velocity maximum at the mean position plus or minus omega a, whereas at both extremes the velocity is 0. You can also get an expression for this velocity. This we got the expression for velocity by differentiating the expression or the function for x. You can also refer to it as the circular from the circular motion. We have our reference particle executing circular motion, let's say p here. This is the amplitude. This is our angle omega t plus phi. We have the projection n here. Now this particle which is in circular motion, its velocity is along the tangent given by, this is from circular motion we already learned the velocity of a particle in circular motion along the tangent is given by r omega, where r is the radius. In our case here we have this as a omega. So if I now take the projection of that velocity which is a omega onto the diameter, this represents the velocity of the simple harmonic oscillator. So because n is the simple harmonic oscillator which is a projection of this particle onto the diameter. What I have done here is I have taken the projection of the velocity of this reference particle onto the diameter. So this is the velocity which is equal to this. Okay, this one. Now this angle here will be omega t plus phi, because you see this is omega t plus phi. This angle is 90. So if this is omega t plus phi, this alternate angle is also omega t plus phi, which means this will be 90 minus omega t plus phi. So that here you have a 90, here you have a 90 minus omega t plus phi, which means this has to be omega t plus phi. So from the small triangle here, you may write that sine omega t plus phi from the small triangle. This is sine omega t plus phi, which will be, this will be omega t plus phi. So the sine will be opposite side, which is what we have as the velocity of this oscillator. So that will be v by the hypotenuse of this triangle here is this a omega. So we have a omega, or you may write v is equal to a omega sine omega t plus phi with a negative sign, because you see this is towards the left, towards the mean position. So the velocity is now towards the left, and therefore minus a omega sine omega t plus phi. So without differentiating, using this reference particle which is in circular motion, by taking the projection of the velocity of that circular motion onto the diameter, you can still arrive at an expression for the velocity, which is what we got in the previous session also. We will now go on to discuss the acceleration of this simple harmonic oscillator, this particle in simple harmonic oscillation. For acceleration, we know that acceleration A is dv by dt, which is v by dt of, we just saw that the velocity is minus a omega sine omega t plus phi. Now I am going to differentiate this, will be sine theta will be, differential is cos theta. When I differentiate this, there is an omega here. So this will be minus a, that omega, when I differentiate this omega I am bringing outside, a omega square cos omega t plus phi. Now this a cos omega t plus phi is what we have as x. So you may also write the acceleration is minus omega square x, showing you that at the two extreme positions, this is the plus a, right extreme. This is the mean position. This is the left extreme. Now at the two extreme positions, when x is equal to plus or minus a, the acceleration will be plus or minus omega square a, which is the maximum acceleration. Acceleration takes the maximum value at the two extreme positions. At the mean position, when x is equal to 0, you see the acceleration is simply 0. No acceleration at the mean position. So acceleration is maximum at the two extreme positions. Okay, now we may also arrive at this equation for acceleration of a simple harmonic oscillator by going back to our reference particle in circular motion. So we have the reference particle P, which is in circular motion. So this is the center, this is the amplitude, this angle is omega t plus phi. The projection of the particle here represents the particle in simple harmonic motion, and this is the x-axis. Okay, now this particle P is under the action of a centripetal force, which is towards the center. So the acceleration is towards the center, and that acceleration is what we call as the centripetal acceleration, of which we have learned in that motion in a plane given by v square by r, or this is also equal to omega square r square by r, which is centripetal acceleration is omega square r, and in our case the radius is the amplitude omega square a. So this is equal to omega square a. So we may write the projection. Now I am going to project this onto this. So this is a centripetal force. If you project it onto this diameter, this will represent the acceleration of the particle. So from this triangle here, cos omega t plus phi is equal to adjacent side, which is the acceleration of the oscillator, by the hypotenuse, which is omega square a, or you may write the acceleration is plus or minus omega square. In this case, it is towards the left, so omega square a into cos omega t plus phi, or a cos omega t can be written as omega square x, which is what we got in the previous, by differentiating also we came to the same expression for acceleration of a simple harmonic oscillator. So even though we have now described a simple harmonic motion in terms of a reference particle in circular motion, you must understand that the particle in circular motion is under the action of a centripetal force, which is very different from the force acting on this oscillator, which is the restoring force. We may also now draw graphs to represent the displacement, the velocity, and the acceleration of this simple harmonic oscillator. Our equations are x is equal to a cos omega t plus phi. This v is equal to minus a omega sine omega t plus phi, and the maximum value will be at the extreme position, at the mean position, which could be plus or minus a omega, and the extreme positions we had velocity equal to 0, and acceleration is minus omega square x. So if you now, which is minus omega square a into cos omega t plus phi. So if I represent the displacement, this is t, and here we have the displacement. If I substitute for t equal to 0, it's a cosine function. So at t equal to 0, we have maximum 1, that is plus a, and then it goes on to take the 0, negative, and then back to maximum. So this will be the minus a. And the maximum displacement oscillates between plus and minus, the displacement will be between plus and minus a. Now if I am going to represent the velocity 0, the maximum value is plus a omega and minus a omega, but it is a sine function. So sine functions will start with a negative sign here. So initially it is at 0. Okay, and at t by 4, this is t by 4, at t by 4, which is sine pi by 2, this will take a minus a omega because sine 90 is 1. So we have from here, it goes on to here at minus at t by 4. Then at t by 2, which is pi, sine pi as you know is 0. So it goes back to 0. Then at 3t by 4, which is 270, that is 3 pi by 2, 270, sine function will take negative values, negative 1, so minus a omega. So this minus into this minus will give you plus, and so this will go on to the positive value and then back here. So this will be represented with, this will be your function that represents the velocity of the simple harmonic oscillator. When we go on to look at acceleration, it's a cosine function just like the displacement except with a negative sign. So when this starts from plus a, the acceleration will be, let me draw it a little higher. The acceleration will be minus a omega square here, exactly opposite to that of displacement here, and this will be, maximum will be plus a omega square. So here, which is at time t equal to 0, your cosine functions take the maximum value. But with the negative sign, it has minus a omega square. Then at t by 4, which is pi by 2, cos pi by 2 is 0. So your function is here at the mean position. The acceleration is 0. Then again at t by 2 we have sine pi 180. So sine pi will be again minus 1. With the negative sign, it becomes a positive value. So it takes the maximum value minus omega square a. At 3t by 4, we have 3 pi by 2. That means cosine functions taking 0 value. So we have acceleration 0 here. And then again at complete time period t, when your particle is at plus a, back to plus a, you see that this takes again the maximum value but with the negative sign. So the acceleration is minus a omega square. So these are the graphs that represent the displacement, the velocity, and this one here represents the velocity, and here this represents the acceleration of the simple harmonic oscillator. So today we have discussed periodic functions and simple harmonic motion. Thank you and good night.